Okay, so earlier we talked about machine learning. We talked about supervised learning, right? Giving a correct answer for each example, right? And we basically said that when we look at this problem, it's actually pretty simple. Supervised learning is basically an example, which could be a vector of x, right? And then output, which is a certain class, usually 1 or 0. So we talked about k-nearest neighbors, which is one very easy to understand algorithm. Right? Basically, you memorize all of your training data, and then you select, based on your test instance, the nearest n or k neighbors to that instance, right? And you make a classification based on this. So this is a really good method. It gives very good performance for things that are quite local. So for example, in the Facebook check-in problem, you can guess if you're nearby an x and y coordinate, and the nearby x and y's are checked into a certain business, then that's likely to be the business that you're checking into. So KNN probably works okay for such a problem. Okay. You can think of other types of decision algorithms. So I'd like you to look at this set of cards. Okay, and the two of you can work together, and the two of you in the front can work together on this, okay? What I want you to do is, one of you come up with a function of these cards, okay? So you're gonna choose certain cards as positive answers, and certain ones as negative, okay? So for example, I might say the 3 of spades is a positive card, for whatever reason. I'm just giving some reason. So I say, positive, negative, 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 positive. And so you might be guessing, okay, black cards look like positive ones to you. Okay? So I would like you to spend a minute coming up with a guessing function, a function that you want to have your partner guess at. Okay? And then you work with your partner and you try to guess each other's functions using something like 20 questions, right? So come up with how you decide what you're going to do. Okay, so you two need to move, the two of you need to think about this. So to be easy, maybe we pick the person on the left, and you see the person on the left is going to come up with a function, right? A function of these 15 cards, which is either going to output yes or no for each card. The person on the right is going to have to come up with at least an initial first guess about how they're going to decide what information they're going to ask you about. So it's like 20 questions, right? So in 20 questions, you're trying to guess which card is it, right? So I can ask, is it red? Is it a number above 9? Is it a face value, etc.? Okay.
So one person comes up with a function that separates the cards in positive and negative, and the other person has to guess the function.
Yeah, it has to guess the function. Of course, you won't get it right away, right? So you have to come up with some idea. So maybe you can say, what would I guess on? Maybe I would guess on, red cards or black cards, right?
Just the cards here?
Yes, just the cards here.
We have 20 questions.
No, I mean, that's the name of the exercise, is 20 questions.
Do you want to ask about which ones? Okay, so if I just read off the mouth with like that, it's positive, negative,
Are you guys doing in the front? Are you doing the exercise? Okay. So while you're doing this, I want you to, if you're done on one side, you can think about what are the criteria that the guesser is using to come up with what tests they're trying out. Right.
You can ask qualitative questions about functions.
Yeah, you can ask whatever questions you want. Yeah. This is just an exercise for you to think about how you choose what you choose for tests. For the win, what's the function?
Mine was prime number.
Prime numbers. How do you use colors? Do you use colors?
No, I didn't.
Okay. Prime numbers. Okay. Interesting. So you can reverse the role now if you want.
So negative, negative, positive, positive, negative, positive, negative, positive, negative, positive, negative, negative, positive, positive. Okay, so 3 of spades is negative, 7 of hearts, 8 of spades, 7 of diamonds, 3 of hearts, 9 of hearts, 7 of spades is negative, 6 of hearts.
How are you guys doing in the front? Still thinking.
Or six. Oh, yeah. Yeah. I don't
Okay, had a good try at this. So typically when you pay 20 questions, let's say with a cousin who's much younger, you pick an attribute and you ask a question about that attribute. So they even have board games like this where you like you try to pick a suspect and all the suspects have different features like glasses, no glasses, hair, no hair, dressed up in yellow, not dressed up in yellow, etc. And so your 20 questions is to narrow it down to a single person. So we're doing a little bit like that here. In fact, the idea is always to for the tester, right, to pick a good attribute, right? So for example, let's say I had a hidden function, okay, and this function is black jacks, okay, so only the 2 jacks at the bottom are positive, okay, but you don't know that, but we could ask ourselves, which of the questions is better, right? So for example, are the correct cards red, or are the correct cards the positive cards in the first row, right? So which of them would give you a better question to ask? Any ideas about that? Which one of these two questions would be a better question to ask than the other? The correct cards is red is a better than this one? Why do you say that? So
it gets you to half the answer.
Half the answer. Okay, both of these are not bad questions. Okay, so if you look at this explanation up here, right, what we're trying to do is pick an attribute that ideally splits the data into what we call like pure subsets, right? Ones that are all positive or ones that are all negative. Okay, so when we do that, it's very easy. We know that we get to at least for one of the decisions that's pure. So in this case, for blackjacks, where this is the positive one and this is a positive, both of these end up with 1/2 of the data set being purely negative, right? So if I say, are the correct cards red? I'll say, no, they're all black. So I've eliminated all of the red cards here, right? 1, 2, 3, 4, 5, 6. Okay, and are the correct cards in the first row? Well, no. So I actually eliminate 1, 2, 3, 4, 5, but I still have to work on the 10 cards down here because I haven't identified which is the right cards yet. Okay, so armed with this information, which of these two questions is better? The first one or the second one, given that I might know blackjacks is the right answer? The first one, right? Because the first one is eliminating 1, 2, 3, 4, 5, 6 answers. Okay, and the second one is only eliminating 5. Okay, it would be a little bit different if you had a different function. For example, if I had a hidden function that was jacks, right? Then you know, there's also this problem, right? I would have one jack here that is red and in the first row, so it might change the values a bit.
Since we're doing supervised learning, won't you already know which are the positive ones and which are the negative ones?
Yes, we do. What we want to do is learn a classifier that can produce the results. Okay, so let's say I'm given this and I want to generalize to a new card I haven't seen before. Okay, then I can try to guess whether it fulfills a function or not. Here, for example, you might have picked attributes for different reasons. You could pick by color, you could pick by picture, whether they're face cards or not. You could pick by location, like X and Y location on the grid, right? All of those are different things that you could decide on, right? Some of you pick by number, like there was a prime, right? So pick by information about the number. Okay, so this idea of picking good attributes is the basis for another type of classification algorithm called a decision tree. And actually, it's probably the easiest to understand because when we make decisions as people with very multivariate input, right, when we have lots of things to make a decision on, we typically don't try to make a decision using all of those features at once. We pick one particular attribute that seems to be important, and we make a decision about that. Okay? So in algorithms, if you're from our SOC and you took 1-10-10 or something like that, you have heard of the idea of divide and conquer, right? So this is an instance of divide and conquer. You have a big data set, but you want to turn it into slightly smaller data sets that are easier to solve. Okay? So for example, many people like to solve the food recommendation problem. Like for example, which pizza provider to cater from, right? So we might be able to ask a question, all right? You know, based on the patrons or the type of pizza or restaurant, I can make a decision. So for the related eating out problem, let's say I have 12 restaurants. And 6 of these restaurants are positive examples of places that people wanted to eat at. 6 of them are negative. I could perhaps choose 2 particular attributes. I could choose whether there are any patrons in that restaurant currently, okay, with the values no people there, some people there, or it's completely full. Or I could pick based on the type of restaurant, the cuisine, right, which could be French, Italian, Thai, or burgers. Okay, so in this particular diagram here, it's clear what we should pick as the attribute. Why? Because if you look at the left-hand side, it's clear that we have two subcases where the decision is clear after I split on this, right? If there are no patrons in this restaurant, nobody in the hawker center eating from those color bowls, don't bother. I won't eat from there, right? On the other hand, if there's some people there and it's not too crowded, it's not full, okay, I'll give it a shot. That's what the training data indicates here, right? But if you look at the right half of this diagram, right, when I divide based on type, okay, you can see that there's actually no decisions that are being made because each one reduces to a smaller problem where the uncertainty is the same. It's still 50-50, right? So for example, originally I had 12 restaurants, 6 positive and 6 negative. After, let's say, choosing Thai, I have 2 positive, 2 negative. It's still 50%. Okay, so that would not be a good attribute to split on because you're not reducing the problem any. You're just moving it down to another level. Okay, so a decision tree works on this principle. It's the idea of reducing problems to smaller problems where each of the smaller problems has more purity in its decision. Okay, you can think of something called entropy or chaos or whatever you want to call it. When we reduce the uncertainty, let's say over here, right? These are clear-cut cases of what you should do, then I'm done. I don't have to do any more work. So if the patrons, there are no patrons in the restaurant, definitely don't go there. If it's full, then I have to choose perhaps another criteria, maybe type, okay, will help me decide whether I should go there or not. Okay? So with that in mind, a lot of classifiers actually implement this type of binary classification, yes or no. But in many cases, the why that we're trying to predict, okay, the label of the thing that we're trying to predict also can be multiple classes. So instead of outputting a binary classifier, we might have to make a multi-class classification decision. So for example, let's say if I ask within all of the School of Computing students, tell me what type of student you are, I might actually make 6 different classifiers. Okay? One classifier that says I'm a computer scientist or I'm not a computer scientist. Another one that says I'm an information systems student, I'm not an information systems student. Okay? So I have these 6 binary classifiers that we've already talked to you about how to make binary classifiers for. Okay? And I run them all, and I take the output that has the highest confidence about saying yes, or the lowest confidence about saying no. Okay? And I'll use that as the judgment call for this multi-class classifier. Okay? They can also be multi-labeled. So for example, there are some problems where you can assign more than one class to it. So for example, select all that apply. If you want to know, for example, what days I go to the gym, I'm making a predictor for that. Okay, I might predict Monday, but also Friday because they're ends of the week. Okay, maybe I'm more likely to do that after I binged eat on the weekends, for example. Okay. All right, so let's go to Kaggle. All right, and take a look at some of the data that we have. Actually, we're going to do it in the browser. You can, at the command line, you can try to do this on your own as well. So we're going to look at some code. We're going to do it together, actually. So I'm going to make a new Python file. Okay, and I'm going to use as a template what I'm going to show you in the first step that we covered partially at the beginning of the first half of the lecture. So I have all of these import statements here. I'm just going to put them all on this side, and we're going to take in the data set. Okay, So if I do this, I have some definitions which I'm starting. So for example, I'm going to read in the data file using the pandas data frame. Okay, so this is data frame here. Okay, pandas, read in the CSV file. Pandas has a very good data structure called a data frame, which is basically like a Microsoft Excel workbook sheet. Okay, so it basically has columns and rows. You can think of it like a database, and there are lots of manipulations you can do on it. Okay, so right now we're going to read in the CSV file that was provided by Facebook. Okay, in this format, because it's comma separated values, we're just going to read it in. Okay, I'm going to skip this one for right now. Okay, and then we're going to get the data. Okay, and so when we save this, we can actually run it already. Okay, so I've loaded in the data. It doesn't do anything special yet, right? That's fine. Then we're going to prepare the data. Like we saw last time, what this does is it tries to take the date format, which is the timestamp, which is in minutes, and then transform it into several columns: hours, weekdays, days, months, year, etc. I'm going to copy all of this and put it here. Okay, so I now have another definition. Maybe I'm going to move that into the definitions above. Okay. And I'm going to run to prepare the data and then print some basic statistics. Okay. So when I prepare the data, I'm actually passing in the data frame by reference. Okay. And then I'm returning the data frame, the transform data frame, into the output, right? And I'm going to save it into this version here. Okay, and I'm going to print the data frame statistics out. Okay, so you can see this version of it now. I have the X, the Y, the accuracy. Those were all fields that we had before, but I took the timestamp and I changed it into this format, right? Hour, weekday, day, month, year. Okay, and this is the output of this is the thing that I want to learn, right? The place ID. Okay, so far everyone with me? All we did is load in the data and transform it. Okay, now we want to apply any of the learning algorithms we've learned, okay? And all of them have the same exact format, right? Basically x, comma, f of x, right? Or equivalently xy, right? So scikit-learn and a lot of other places, they use the xy standardization. Since x are the observed inputs, all the variables that you get to take a look at, and y is what you want to learn, the label that you're supposed to learn based on supervised examples, which you have to predict for a test case. Okay, so here we go. I'm just going to copy it in here. Okay, scikit-learn calls this fitting. Okay, fitting a model to the data. Okay, so a decision tree in particular has a couple of parameters, okay, which you can customize. So for example, min sample split, okay, this says I need at least 100 examples if I set this to 100 for a node in a tree to be split. So a node in a decision tree is exactly what we saw in the slides, right? It says here, for example, I have to have 100 observations, okay, that I can make a judgment call on before I'm going to split it into component parts, okay? Now, earlier I said the more pure the resulting classes are, the better. So these two are pure, but sometimes, many cases, you don't want to split on too many nodes all the way down for reasons of overfitting, which I'll explain later. So we'll stop prematurely. So even though, for example, this particular thing up here, can I drag this out of the way? No. Okay, but basically, even though this class isn't pure, I might decide, okay, I don't want to split further. I need to call all of the cases which I get to this section as no, false, red. Okay, because that's the majority class in that part of the tree. Okay. So that's what this min sample split means. Okay, and I have to have something to seed the random number generator, which is going to help generate random numbers for this algorithm. So I just set it to some seed. Okay, so I'm going to give it the list of features that I'm going to use to do the prediction, which is basically all of the features that I have. So I indicate from the data frame all the columns that I want to do the prediction on, right? I don't want to include the label itself, right? The place ID, because that's what I'm trying to learn. So I don't provide that as the data of the observations. This is my X, right? These features are my X, okay? And for Y, I'm using just one column, right? I want to output the place ID, okay? So basically I have to make these two declarations. I need to declare part of the training set, the data frame, to be the labels, and I have to declare some of it to be the observations, okay? With that, I'm done. Basically, I have my big X and my small y, right? What I want to predict and what I have to predict. Then I just call the decision tree classifier here with those parameters, and I have a model. Okay? Now, this just declares a model. It doesn't actually do anything yet. So the next thing I have to do is train the model. So I do that by calling this one thing here, model fit. Okay? And it'll learn the model. Okay? So I'm going to run that. Okay, and now I have a learned model. I haven't done anything with it, but it actually computed a decision tree model for me. Okay, so the next thing I want to do is maybe look at what came out, right? I want to see whether it makes any sense. Okay, for this particular model that we're training over the Facebook data, it might not make a lot of sense, but there are lots of tutorials within the scikit-learn library, or even in Kaggle, which you can use data sets that are less obfuscated to make a little bit more human sense. Okay, so I encourage you to use the IRIS dataset, which is a very, very popular dataset that practically every machine learner has used. Okay, anyone who's learned machine learning, I should say. Okay, and also the Titanic dataset, which is part of the Kaggle competition. Those are good datasets to try on. So the Titanic dataset has some information about the survivors and passengers on the Titanic, and you have to classify whether they made it or not. Okay. Okay, so maybe we want to write the tree out so that we can create a visualization. To do that, I need some other methods. Okay, so I'm just going to take them here from the other file and then dump them into the defines that I have earlier, and hopefully this will work. Okay, so I have now here a decision tree file that represents the output. Okay, it's written in dot format. Dot is a graphing library, but I didn't ask you to install it. Okay, the reason is it's sort of archaic. It's not very new. So there are better libraries to do this, but this is the one that comes easiest. So we're going to use a utility to do this online, and I'm going to have to find out where it is. Oh, not this one. The GitHub document. Where's that? Give me 1 second here. Okay. Okay, so we're going to use this utility out there, which will allow you to take a dot output, like for example this one here, and then run it. So it'll produce something like that if you're doing those types of graphs. We're not doing that. We're using a decision tree. So we're going to output this file, okay, and upload it. Actually, I think I can just choose here. So we're going to run that and take a look at what it outputs. Okay, while that's going, we'll keep on going on the examples. Okay, so now we have a model. We've prepared the data. We've done the decision tree. And maybe now what we want to do is try it out on some data. Okay, so let's take a look at the output that we're going to get. So, okay, if you look at this line, the first part is we're using the model to predict on some data. Now, this is not fair. What does this say? Train data. Are you allowed to test on the training data? You can, right? But it doesn't make a lot of sense, right? What does it say? Oh, I've taught you what 2 plus 2 is. Now tell me what 2 plus 2 is, right? So of course, any learning algorithm worth its salt should get very good values in this. Almost always this is 100%, but there are many reasons why it's usually not 100% in practice. Can you tell me why? What are some reasons why a training algorithm might not give you 100% on the training data? Okay, so maybe it's ignoring some outliers. That happens a lot. Okay, maybe our input is noisy. So for example, I give it two x and y coordinates. They're exactly the same thing, but they checked into two different places. Okay, I don't know why. It's just like that. Okay, so when there's noise, there's no way you can get 100% of classification accuracy. Okay, so in any case, I'm doing this faulty test here, which basically says I'm going to see how well my classifier works on the training data. It should work pretty well, right? If you memorize your training data, you would get 100%, except for the cases where there's conflicting noise. Okay? And then I'm going to be able to output, let's say, metrics based on the training performance. Okay, and so you can see here what the training performance is. As I told you before, in the first half of this lecture, we have 191 unique place names in this data set. Right, so this is pretty long output, and you can see here there are quite a lot of singleton or less than 10 instances. Like all these 5 places, they have less than 10 check-ins. Okay, so you can see our classifier is not able to guess any of these because they're so small, and instead tries to, of course, make guesses for the larger classes. So here we have some predictions of people checking into 127 something, some predictions on 214, other ones on all of these other ones here. Okay, so that's the decision tree. So I thought I had it here, but maybe we didn't do it. Let's try that again. Okay, so here's the root of our decision tree. Okay, basically it looked at all of the features that we provided it, and it decided the most informative feature that's going to give me more pure subsets is whether the y value is less than 0.142. Okay, it's in the first half of the data set. That's what it decided. So this has two possible consequences, yes or no, right? So the no values are over here, and the yes values are over here. So for example, if indeed the y was greater than that, okay, then I'm going to check again y. All right, for this particular test here, I'm going to say, is the y greater than 0.1817? Then I'm going to continue going to the right, otherwise go down, and then I do some more splits. So it seems like here, for at least the first couple levels of this decision tree, the y value seems to be pretty indicative of what place was checked into. Okay, so in the first half of our lecture, we showed you a Python notebook where somebody said basically that the x values are strewn all over the place and the y values are pretty constant. So this agrees with the analysis that was done earlier, that y values are pretty set in this data set. Okay? So then other things start to come across later on. So for example, here it seems like the variable of month starts to play a role. Okay, and then year, and then hour, etc. And so you can see at each point we're getting less and less samples that are relevant at each of these nodes, right? And then it's approximating this idea of asking the 20 questions until you get down to a size where the sample size is small enough that we have to make a decision. Okay, so here are all the decisions on this sample. Okay, I have 15 samples here. 9 of them go to a particular check-in location. Some of the other ones go to these miscellaneous places, wherever they are. Okay, question?
How do you construct the decision tree?
How do we construct the decision tree? It's based on the entropy of a node. Okay, so for all of these values, so for example, if you look at the top thing here, basically it needs to make a decision about the attribute that's picked and the value where it is doing the cutoff. Okay, so it's looking through all of these parameters and finding a test that's going to split the data set as best as possible into two subsets, each of which has less information than before. The lower the information, the lower the entropy, the higher the purity, the more consistent the decision will be. Okay, so you want to know the technical details, take the module next sem, or take Coursera. Right? Andrew Ng has a fantastic machine learning course, which I will be taking in order to teach the course at NUS. Okay, so that's the short answer to your question. Okay, with other classifiers, there are other ways. So each classifier has different ways of making decisions. We talked about decision trees now. We talked about k nearest neighbors, right? So those are two classifiers that we've touched on. Okay, so basically after doing this, we have the output on the training data set. Okay, the training data set is actually, the classifier is not particularly good. We are getting 0.46, 0.51 overall for precision and recall. We're not going to teach you what precision and recall are here. Okay, again, these are metrics used to define machine learning. Okay, but basically the idea is these scores range between 0 and 1. Okay, 0 means you're doing atrocious, you're not doing any work. Okay, and 1 means you're doing perfectly. Okay, on most problems with, let's say, k inputs, k labels, then 1 over k is the expected value of random guessing. Okay, so for example, I have positive and negative classes, and let's say I have even number of positive and negative examples, then making a random guess should get you 50% right most of the time. Okay, so that's the idea. Here we have 191 classes. So if we expected a uniform distribution of all of them, then you'd get about 0.5% correct on average, right? Because there are about 200 classes, right? So each class is worth 0.5%. Okay, but you can see here from this right column, it's not very uniformly distributed at all. There are some that are much higher than that. Like for example, there was a couple here with 700 instances. So those should be pretty easy to guess, right? In fact, if you took the single class that's most common in out of all of these, for example, let's say 737 is the majority class, the one that has the highest number, then by default, if I only guess that, I should get 737 out of 3,901 instances correct. Okay, maybe about 1/4. So you would guess your score should be about 0.25 by random guessing. Okay, by just saying everything, you're just going to check into here. Everyone's going to check into Changi Airport because they have to get out of Singapore eventually, right? That's the idea. Okay. All right. So that's this classifier. We haven't finished though, so we printed out some metrics. Basically, we printed out the classification report and we printed out the confusion matrix. The confusion matrix is this part at the bottom, okay, that is supposed to show you what things got confused for what other things. You can't make up much detail here, but basically along the diagonal are the classes that are correct. Anything off the diagonal means the class was wrong. Okay, so let me say, for example, what this coordinate here means. This means the first class was guessed as the first class. Okay, actual first classes were guessed as the first class. Okay, so because the first class in this instance happens to be a very small minority class, none of the instances were guessed as the first class. Okay, on the other hand here, we have 19. This corresponds to the very last class. And you can see that here is the very last class. Actually, there were 33 instances of them. We guessed 19 of them correctly. Okay, so 33 divided by 19 is actually called the precision. That's 36%. Okay, so we have some idea how to interpret this. We look at the confusion matrix when we have a small number of examples or a small number of classes to see what things get confused for what. Okay, so whether, for example, IS students get misclassified as CS students, then I want to know how often that happens and how I can fix that. Okay, the last thing what we can do is actually try to use the predictor that was learned on new data. Okay, so we're going to do that here. Okay. Okay, so here what we're going to do is we're going to get the test data, all right? And we're going to predict on the test data. Now the test data is a little bit different from our training data. It has no label. It has no classified place names. So we're going to predict the classes where we're going to go, right? Oops, I think I forgot to add something at the beginning. Let's go do that. Oh, I forgot to import the other mod definition. Let's do that. Okay, and then what you can see here is that when I do the prediction, I have predictions for each input. So this is the first input, the second input, the third input, all the way into the last input. It's basically an array of place IDs which the classifier is guessing. Okay? All right, so this is how I would actually use a classifier in practice. Okay, if you have an orbital project, you want to use machine learning. Often where you apply the machine learning is on the back end, on the server. Okay, you don't do it on a client. Like you probably don't want to do it in JavaScript. Okay, you don't want to do it on your Android device or your iPhone, but you send the data that you have, if it's on the client, back to your web application, your server. Okay, and then on your server, you invoke something like what we're doing now, that given a model that was already created, okay, you would run the predictions, right? You would get the test data that could be from the client, okay, transform them into the format that you need to use the classifier, okay, and then do the prediction, and then take the output of the predictions, instead of writing it to a file, maybe transform it into a particular data format that your client will understand. For example, change it into a JSON object, and then send it back to the client and have the client do something with it. Okay, so almost all cases, the machine learning module, all the heavy lifting, the classification, is done on the server. It's not done on the client. Okay, now there are exceptions to that. So for example, the decision tree that we saw, actually, it's no more than if-else then statements. Because if you think about it, each node is just testing a particular value, and then using that value, deciding other tests until it gets to a decision, and that decision is then given to the client, right? So in actuality, you can take a decision tree that's learned, and it's basically a bunch of if-then-else statements, and then send it over or imbue it as part of the software written in your package, then you can use it right away. Okay? So that's how I would deploy it in practice, right? This is for deployment. Now, an obvious question that you might ask is, how well will my deployment work, right? So we can train on the training set, we can test on the training set, and we already know that's artificially, you'll get artificially high results. We can test on the testing set, but we don't know how good our classifier works on the testing set, right? Because now I've done predictions. Those predictions, I have no idea whether they're correct. So what can I do? What can I do to fix this? Any ideas? We basically have two things right now. We have a testing set which has answers in it. We have a training set which doesn't have answers. Right? Somehow we need to have the test set have answers too. How do we get there? Perfect. We're going to take the training set and we're going to cut it up into parts. I'm going to discard my test set. Forget about it. It's not labeled. I don't have answers for where they checked in. So it's not useful to me. Okay? But what I'm going to do is I'm going to take the training set and cut it into two parts. A training set, and a test set. Okay? I'm going to train on the training part of the training set. I used it 3 times. Okay? And I'm going to test on the test portion of the training set. Right? This is fair because I'm telling you I've cut my training set, which has answers, into 2 parts. One that I give the machine learner to learn from, and another part which I keep reserved, hidden, to see how well it does. Okay? And then I can say, if my test data looks like my training data, then I can say I have a reasonable amount of confidence that it's going to do similar to what I've done, because I've cut my training data into parts. Okay, so remember at the very beginning of our file, when we talked about this very early on, right? We said induction, right? Is the past going to be the same as the future? Will the sun rise tomorrow if it rose today? So this comes back to the same thing. If we believe our test data looks like our training data, then induction is actually sound. Okay? If our test data isn't anything like our training data, like I gave you the example, NUS lecturers, they give you all these nice tutorial questions, very well formed. You find the final test, good Lord, nothing like what I learned, right? Then of course you're going to score badly, right? Hopefully it's not usually the case, okay? But it's the idea behind that, okay? All right, so this comes to what we were talking about. We're going to try our new function, our machine learned model H, hypothesis function, on a new set of test examples, right? And we can graph what's called a learning curve, which is the percentage of things that we got correct on the test set as a function of the training set size. Okay? As I give you more and more examples of practice problems, hopefully you get better and better at doing it. So this is exactly what happens in machine learning too. The more examples you get, the better the model that's getting will get generalized, and the better the performance that we'll get, right? This is why you always hear about all those big companies like Facebook, Google, Grab, whatever, taking all your data, using machine learned models, and then making their services even more valuable, right? Okay. So that's exactly what we're going to do, but we're going to carry this idea a little bit further. Instead of a training and testing set, we're going to do something called cross-validation. Okay, it looks like the pizza there, all right? Basically, we're going to take a very large pool of examples, all labeled, okay, so maybe 3,900 cases, okay, in our training data. We're going to cut them up into parts, okay? We're going to cut them up into, let's say, K parts. Okay, we're going to take K minus 1 of these parts and use them as training data. Okay, I'm going to take the KF leftover part, use it as testing data. That will be run iteration. Okay, but you know, from that one test, that's okay. But I'm not really sure whether everything generalizes. For example, if I split my data a certain way, maybe I didn't get to see certain test cases that I should actually see. Okay, so it's not a very stable test. So I'm going to repeat this K times, right? Because I have K slices. Okay, so I'm going to at each turn say this is my test data, then this is my test data, then this is my test data, then this is my test data, etc. To go through all of the pieces of the pie and conduct this training and testing work. Okay, and then by averaging all of these results, then I have a pretty good idea of how well this classifier will do on new instances that are very like the training data that I have. Okay? So scikit-learn makes that absurdly easy to do. So we're going to look at that. Okay, let's see, where is it? It's here. Cross-validation. Okay? So it says here, learning the parameters of a prediction function and testing it on the same data, which we just did, right? We ran the predictor on the training data, is a methodological mistake. You all said so yourself. A model that would just repeat the labels of the samples that it's just seen, right? So it can get a perfect score, but because the classifier is so tuned to the training data, it won't have any generalization on new things. It'll look at a new data point and says, I have no idea about this. I'll just spit up some random answer. Okay? So this is called overfitting. So what we try to do is run a machine learner in such a way that it avoids overfitting by generalizing. Do you remember in the decision tree learner, we said there was a variable that said when to stop splitting nodes. Okay? This is what that purpose is for. Because if I want to split nodes indefinitely until things are pure, I can always get 100% accuracy on any training data, as long as there's no noise, right? Because I can always split until everything is pure, okay? But by doing so, my training data, my decision tree might be very complex. It might have many, many nodes in it. A lot of them which are not really generalizable. They're capturing some regularities of the training data, but not regularities of the problem, okay? For this reason, a lot of decision tree algorithms have this early stopping criteria. It says, you know, if I'm going too deep, I have too many tests, you know, forget it. I'm just stopping. You know, even though it's not pure, I'm just going to give you an answer. Because I believe if I go all the way down, you know, I'm capturing some irregularities, not capturing regularities anymore. Okay? So what we do is we do this training test split, but we're going to do it on cross-validation, right? So this is what we just talked about, right? The following procedure is followed for each of K folds, right? A model is trained using K-1 folds as training data, and the resulting model is validated on the remaining part of the data, and used as a test set to compute the performance measure such as accuracy. Okay, so we can do this by following something like this, where after we declare the classifier, CLF here stands for classifier. So I take any classifier, it could be a decision tree, it could be what's called a support vector machine. That's what this one is here. Doesn't matter. Okay, and I throw it into a cross validator. Okay, that says I'm going to carry out here 5-fold cross validation. Okay, I'm going to conduct 5 experiments where I cut the data set into 5 parts. I train on 4/5, I test on 1/5, repeat, rinse, and return 5 times. Okay, and then I will have these scores here, and then I can average them and get an output. Okay, so we're going to do that. Okay, so instead of doing it this way, let's go back and take out some of the model. So at this point, you have pretty much what is described in the Git repo as learn 01. Okay, but we're going to go to learn 02, which gives you a lot more classifiers to play around with, but more importantly, gives you the cross validation. Okay, so I can do something like this. Okay, and then do that instead. Okay. Okay, and I think I have to do some imports that I'm missing. I'll try to do that. Okay, so I've imported the cross-validation library in sklearn, and then I've gotten rid of all the classification gunk that I had earlier, and I'm just creating a classifier with this line here, and then calling cross-validation to do the work. Okay, this one I did 2-fold cross-validation. Let's make it 5. Okay, and then I'm just printing out some accuracy measures here. Okay. Let's see whether that works. It did. Okay, so I did 5-fold cross-validation. I get an accuracy of 0.42 plus or minus standard deviations, 2 standard deviations of 0.6. Okay, so that's how I do it with the decision tree. Okay, so there are other things you can definitely use in the scikit-learn library. There are lots and lots of classifiers, so you can look them up. Quite a lot of my FYP students have tried a lot of these. So even early on in Orbital, you can try to do that. So here's our decision tree. You can see a little bit about why decision trees are interesting. I forget how to zoom. Okay, but anyways. Okay, you can see the decision surfaces that decision trees make are linear. They're straight lines because basically they're choosing a single attribute, okay, with a particular value and say, I'm going to split the data set here into 2 parts or n parts. Okay, so you can see when the data set that you have is separable on these dimensions, it works perfectly fine. But when the data set is not separable because there's a lot of interaction between variables, it ends up making a big mess of them, right? Like you can see here, this particular random forest, which is based on decision trees, also has to make very many complicated decisions in order to come up with the decision boundary that's sort of like S-shaped. You can see here that this particular data set is more like an S shape. Okay, so other systems can do that better and some worse. And then again, depends on the model that's being used. Okay, remember earlier we saw polynomial fitting, right? Linear regression using a line, quadratic polynomial, a cubic polynomial. Those all differ in the amount of parameters that they have. So something simple like a linear SVM basically has only 2 parameters. It's the same as a decision surface that has only got 1 space on it. Okay, but the decision tree is quite complex. You can see what it's doing is it's using each of these lines here is basically a node in the graph that's splitting on things. Okay? So with the more complicated decision surfaces, there's more model bias being built in. So you can see all of the different types that are around here. Okay, well, you know, from a point of view of a practitioner, rather than someone who wants to learn the theory, we don't care what the classifiers do as long as they do their job well. Okay, so why don't we go back and try to test them out, right? Okay, so I've done cross-validation. Using decision trees, right? But I could use any number of other methods, and they all basically in scikit-learn take the same format, right? You have to declare a model, okay? And then after that, either send it to model fit, which will create the model, or send it to cross-validation, which internally is going to call the fitting process. Okay? So instead of, let's say, decision tree classification, okay, let's say I want to use nearest neighbors, right? We learned about that. So all I have to do is add that here, right? I'm going to add it to my classifiers part. And then when I get to the bottom here, I'm just going to change the classifier that I'm going to use. Let's see, where is it? Here it is. K nearest neighbors with free neighbors. Okay, dump this in, zoom that one out, and run, right? It's not very good. Pretty terrible compared to decision trees. And you can tune it, of course. A lot of people will, just run a loop, try everything. Okay, run auto classify with lots of different parameters and see what works best, right? So this actually works a little worse when you only have one neighbor, but you can try, let's say 5 neighbors, see whether that works better. Okay, so a little bit better. Okay. So that's how you use all the different classifiers. So in the second learner file that I committed, you can see quite a number of these. Okay, so we have decision trees. We already used that before. We have K nearest neighbors, which we just used. There's another very famous machine learning type, which works very well for high dimensional data, which means you have maybe instead of 4 different columns, maybe you have 1 million different columns. Okay, that's called SVMs. They work very well for that. Naive Bayes is another one that you'll learn in the Foundations of AI, which I used to teach, and we'll go over it again in the machine learning. This is also a very simple algorithm. It works usually for medium-sized columns that are all not too that all the variables are independent of each other. They're not cross-correlated very much. Okay, and earlier in I think our dinner time, one of the ladies here asked about, is it common to use more than one classifier to make a decision? And yes, that's very, very common. That's called an ensemble method. It's when you group several classifiers and you find some way to get them to come up with a single answer. So just like we did for deciding to order a Pizza Hut, I might poll all of you and say, where do you want to order from, right? Or where do you think this person's going to check in, okay? So all of you vote. I take the majority class and I say that looks like everyone thinks they're going to check into, I don't know, 212. So I'm going to say it's 212, okay? There are many different ways of combining methods together, okay? Many of these work with what are called weak learners, which are learners that don't do very much but produce a little bit of signal over the noise. And so 2 of them that are very common that you'll hear about are random forest and Ada boost. Okay, both of them basically start with the same idea. You start with a very dumb classifier. Okay, it makes certain mistakes. It gets certain things right. So for my second classifier that's going to build on top of the first classifier, I want to correct for the mistakes that the first classifier made. So what I'm going to do is I'm going to look at the residual instances which I got wrong the first time, and then tune the classifier to do better just for those instances. Okay? I'm going to do this repeatedly. So I might have maybe 100 different classifiers, just like I might have 100 nodes in a decision tree. It's basically the same type of algorithm. Okay, and then I'm going to recurse, and then finally arrive at a decision that's the amalgam of all of the different component classifiers. Okay, so ensemble methods tend to do better than single methods because, of course, there's a lot more knobs to tune. But of course, it's also, as I told the lady, harder to understand why they work because now there's so many knobs to understand. You don't really understand why the classifier produced this result, right? So, for example, I asked you why you guys decided to order at Pizza Hut, right? So actually, we know there was somebody in the audience that says, "Oh, Pizza Hut's fine." Then we decided to go with that because all of you were like following that person and said, "Oh, Pizza Hut's fine." Okay, but for a lot of complicated cases, when each classifier is making a decision, you have to explain each of those decisions individually, then ensemble it to get a result. It becomes harder and harder, less and less transparent what the classifier is doing. Okay? Okay, so we can use an ensemble method like random forest. And then do a prediction here. It doesn't do any better than the decision tree, only 20%. And so you can try with various other reasons here. Okay, so with that, I'm pretty much done. I don't think there was anything else I wanted to cover. Yeah, that's the last slide. So, oh yeah, I did want to cover Seaborn. So one thing that you should be doing at the end of things is to try to analyze your data. So earlier, when we looked at some of the visualizations in Kaggle, okay, let's go back out to where? To here. Okay, you saw quite a lot of these exploratory data analysis in the IPython notebooks that you saw here, right? So they can do all this plotting and things. Okay, you should, if you're doing machine learning, start to try to visualize the data that you have. Okay, so a nice library that's just recently come out this year is called Seaborn. It's created by a Stanford student. And you can use it too. It's not hard to do. Let's see. So you just import it as SNS or whatever variable name you want to give it. Okay, and then you can do any of these types of color plots here. So I'm just going to dump it in and show you how it works. So let's say I don't care about the classification. I just want to do some data analysis. And I'm going to have to import certain things, so I'm going to do that now. So Seaborn is built on top of Matplot library, so you need both. Oops, I think I forgot to save. So it'll produce you a figure like this. So this is our data set of all the check-ins. Remember, we took the data set from 1.1 to 0.2. So this is 1/10,000th of the entire data set. And we're just plotting the X and Y values here. Okay? So you can do this, and you can see a lot of them are gathered down here. So you might expect some of the data down here to be harder to tease apart, right? The ones over here seem less dense. Okay. So you can do join plots like the one I'm doing of anything. So for example, I want to do one of the X and hour, and I can do this. So you can see 24 bands here, right? And the nice thing about Seaborn is it will not just give you this thing over here, but it'll give you the histograms on the side. So here you can see, for example, this is the hour of the check-ins, right? So here we have 0 hour, so that's 12 midnight, all the way until 6 a.m. So things, check-ins go down as you go into the early hours. Hopefully, that means people are sleeping, right? And then they peak maybe around 8 o'clock at night, okay, when most people are eating or doing funny other things, right? Okay, and you can see the x-axis over here and how they might correlate. Okay. So Seaborn actually has quite a lot of nice visualizations, so I'll just show you that. So it can plot distribution plots with a normal line to it, histograms, some nice figures, like here's a hex bin plot. So this is the same type of plot, but you give density, so it's various grayscale levels, especially if you have a lot of data points, like say you have 1 million data points, then plotting the individual data points is not helpful, right? Because they'll all be plotted on top of each other. So using a hex bin plot or anything like this will be useful for that, okay? Or any of these other ones. Like, for example, I want to visualize all every two-dimensional combination together on one plot, okay? I can do that, right? It's actually just one line of code, SNS pair plot, and then the data set. Okay, so I can do this on the data set that we have, but because we have a lot of data, it's not going to look very nice, but I'll do it anyways, just so that you have an idea of what it is. Okay, so we have to wait for a while while it's checking away, and then we'll get this too big to fit on my screen picture. Okay, so these are all the data points that we have. We have about 9 dimensions or so, so you can take a look at all of this data at once. Right? I don't even know how to scroll this screen. Yeah. So if you can make sense of the data, that's great. If you can't, don't worry about it. You should pick some dimensions. You should add some other information into the data set. So for right now, for example, we only have blue colors, but you might want to take all of the place names and assign them an RGB value. Then you can maybe visualize this a little bit better than what we've done today. Okay, so that's my machine learning for newbies tutorial. I hope it was worth your while to come. If you have any questions, I'm happy to stay back and answer them for you. And I look forward to seeing some of you maybe in the future in the machine learning class. Or, you know, hopefully you can incorporate machine learning into your own work or in your data analysis, especially if you happen to be a business analytics student. This is really your bailiwick, you know, the stuff that you should know. Okay, thanks very much for coming. And with that, we'll close the webcast.